Welcome to the deep dive. If you're the kind of listener who, you know, loves to gain thorough knowledge without being overwhelmed by endless white papers, you're definitely in the perfect place today.
Absolutely. It's great to be here.
Because our mission today is to really demystify this hidden but incredibly adaptable layer of the semiconductor world. We're talking about FPGAs, field programmable gate arrays, and of course the EDA tools that actually make them function.
Right. The electronic design automation tools,
Yeah.
which are just as important as the chips themselves.
Exactly. And we're basing all of this on a really comprehensive exploration of the book FPGA EDA, Design Principles and Implementation by Kai-Hui Tu and colleagues.
Right.
And the best analogy I pulled from this right away is that FPGAs are basically the electronic Lego of the semiconductor world.
What's fascinating here is that, we normally think of computer chips as just carved in stone. A standard ASIC rolls off the foundry line and it's permanent.
Right. If there's a flaw, you just have expensive sand.
Exactly. But an FPGA gives you these pre-designed hardware blocks that you can literally assemble in the field via software to create entirely new digital circuits.
Okay, let's unpack this.
Yeah.
Because FPGAs have evolved massively. I mean, if we go back to the grandfather of them all, the Xilinx XC2064 back in 1985.
Oh, yeah. A true classic.
It had just 64 programmable logic units,
Yeah.
which seems so quaint now.
Just 64. Yeah.
But it literally changed the world.
Yeah.
It actually earned a spot in the IE Chip Hall of Fame. But to make this whole Lego kit work, we need to talk about the plastic of the Legos, right? The memory.
Yeah, the configuration memory is where your custom design actually lives. And the engineering trade-offs there dictate what the chip can even be used for. Most mainstream chips use SRAM.
Which is volatile.
Right. It's fast, it's low cost, but volatile, meaning you lose power, you lose your design, you have to reload the bit stream every time it boots up.
Which is totally fine for a data center. But if you're putting a system in a high radiation environment, like a satellite in low Earth orbit, an SRAM cell can just get flipped by a stray cosmic ray.
And suddenly your routing matrix is broken.
Exactly. Which is why engineers opt for antifuse FPGAs for aerospace. You are literally burning microscopic fuses to set the logic.
You lose the reprogrammability, but it becomes virtually immune to those radiation-induced soft errors.
And then there's a whole other end of the spectrum, like edge computing and the Internet of Things.
Where power is everything. You can't afford the static leakage of SRAM there, but you still want it to be reprogrammable. So we're seeing this big push toward emerging tech like RAM and MRAM.
Because they hold their state without drawing power.
Right, and they don't consume extra transistor area either. They can be stacked vertically over the logic. Ultra low power for IoT.
But the logic blocks themselves haven't stayed stagnant either. We've completely moved past just basic logic gates.
Yeah.
Today, we have modern heterogeneous tiles.
Integrating hardcores right into the fabric.
Yeah, instead of forcing engineers to build an entire processor out of tiny logic blocks, vendors started just embedding an actual hard ARM CPU directly into the chip. I think Altair Excalibur first did that around 2000.
Which completely shifted the paradigm. And today, you look at something like the Xilinx Versal from 2019, and you have embedded GPUs, dedicated matrix computing tiles for AI workloads.
And there's this brilliant Bugatti Chiron analogy from the source text to explain how this is used today.
I love that analogy. It's the perfect visualization.
Right, so imagine prototyping a real Bugatti using a Lego Bugatti. You can test the aerodynamics, maybe the suspension, but you can't test its top speed.
You're not breaking any speed records with a plastic Lego engine.
Exactly. To do that, you'd need to take your Lego frame and insert a real function combustion engine into it.
The scalar computing tiles.
Yes, and real rubber tires.
The analog circuits.
Right. And that is exactly how modern FPGAs are used to prototype advanced ASICs. You mix the flexible Lego logic with real hard silicon engines to see how the final chip will perform before you drop $50 million on a mask set.
But doing this, building a design that complex with millions of gates and AI tiles, you can't do it manually. It's an impossible spatial puzzle. We need EDA to handle the blueprints. It is truly the mother of chips.
So let's talk about how that EDA software actually translates human ideas into hardware. It's basically a massive pipeline of abstraction, right?
Yes, going down level by level.
So at the high level, you're writing in C++. The EDA pipeline steps that down to the low level. using XML or JSON and Verilog,
And then it drops down to the machine level.
which is the binary bit stream.
Exactly. And if you're actually fabricating the chip itself, you go one step further to the physical level, outputting those GDSII layouts for the foundry.
And to make this whole translation work, the EDA tools rely on structure models, the logical resource structure, and the configuration bit structure.
The LRS and CBS. This is a massive mapping operation. The tool takes a logical address,
Like what the component actually does.
right, and maps it to a physical address,
Right.
where that specific bit lives in the configuration protocol to make the routing connection happen.
Here's where it gets really interesting, though. It isn't just about successfully mapping the logic. The EDA tool is constantly performing a balancing act with the holy trinity of chip design: power, performance, and area, PPA.
And those three are always fighting each other.
Let's start with power.
Power is a massive headache at smaller nanometer nodes. You've got static power, which is just transistor leakage, microscopic currents leaking even when the chip is totally idle.
And then dynamic power.
Right, which happens when the logic states actually flip, charging and discharging the interconnects, plus short circuit power.
So how do the tools actually estimate that dynamic power before the chip is even running?
Well, you can use simulation-based techniques. You feed massive files like SPICE or VCD files through a virtual model. It tracks every single net flipping.
Very accurate, but I imagine the compute time is brutal.
It is, which is why we often use probabilistic-based techniques instead. It relies on static probabilities and transition densities. You get a surprisingly accurate estimate way faster.
That makes total sense. Now, what about performance? Which in hardware terms is basically just timing. How do we ensure signals arrive exactly on time?
That's tough. We use static timing analysis, or STA. Dynamic timing analysis, where you actually simulate the data moving, is just dead for massive designs. It takes too long.
So SDA just looks at the math, the physical speed limits of the routing wires and the logic cells.
Precisely. But standard deterministic STA has a flaw. It assumes the absolute worst-case scenario for every component along the path.
Because of manufacturing variances.
Right.
Some transistors are a little faster, some are slower.
Exactly. And assuming the worst for everything leads to massive over-engineering. You burn extra area and power for no reason.
So we use statistical STA instead, SSTA.
Yes. SSTA treats those delays as probability distributions. It's a much more realistic picture.
And within SSTA, there are two methods. The path-based method, which is exhaustive and great for small designs.
And the block-based method,
Right, which uses a breadth-first search.
which is highly scalable and perfect for the massive complex designs we see today.
Okay, so that covers power and performance. But what about area? Even on an FPGA where the physical chip size is already set, you need to know how many resources your design is going to eat up.
Right, and if researchers are designing new FPGA architectures entirely, they need to estimate the silicon footprint without spending weeks drawing a physical layout.
Which is where layout-based techniques or the minimum width transistor area model come in, the MWTA.
The MWTA is crucial. It normalizes everything into a mathematical unit based on the smallest printable transistor. You just sum up the math and get a highly accurate area estimate instantly.
If we connect this to the bigger picture, creating a full custom FPGA layout from scratch, plus the proprietary EDA software to map it, takes years. It's a massive bottleneck for research.
It's basically impossible for an academic lab to do alone.
Right. And this is where open source, semi-custom EDA frameworks are stepping in, tools like OpenFPGA.
They're completely changing the game.
Because they generate the Verilog netlists and test benches automatically, compressing years of work into days.
But there is a huge verification hurdle there. The test bench dilemma. Just simulating the bitstream loading process for an 800 kilobit file takes 24 hours of raw compute time.
What they call a full test bench. You literally hit compile, go home, sleep, come back, and it's just finished loading. It hasn't even tested your code yet.
It's agonizing. So the clever workaround is the pre-configured test bench. It completely skips the loading phase. It forces the SRAM cells into their configured state instantly so you can test the operating phase right away.
That's brilliant. But let's keep it real for the listener. Semi-custom isn't perfect yet. Looking at the data in the text, if you compare a 40 nanometer semi-custom FPGA to a commercial Stratix's Fieth, the results are mixed.
Yeah, the area is fantastic.
Right. The custom cells are 42% smaller, but the path delay is up to 30% slower.
And that performance gap just highlights how hard it is for academic CAD algorithms to catch up to the proprietary, highly guarded routing algorithms used by industry giants like Intel and AMD.
It takes decades of optimization. So what does this all mean for a normal software developer? Someone who only knows C++ and wants to use FPGAs.
For a long time, you couldn't. FPGAs were locked behind hardware description languages like Verilog. But high-level synthesis, or HLS, changes all of that.
HLS bridges the gap. It actually compiles standard C++ directly into a parallel digital circuit.
It's incredible, and it does this by scheduling the circuit. It translates the code into a control data flow graph.
The CDFG. And then it schedules every memory fetch and math operation into clock cycles.
Exactly. You can use ASAP scheduling as soon as possible to minimize latency, or ALAP scheduling as late as possible.
Which introduces this great concept of slack. If an operation has slack, it means it can wait a few clock cycles without delaying the final result.
Meaning you can share resources. You don't need to build two hardware adders if you can just schedule the additions on different clock cycles using one adder.
Saving silicon area without hurting performance. And HLS compilers are also amazing at optimizing loops in software.
Oh, polyhedral analysis. It analyzes the memory dependencies of predictable loops, which we call static control parts, or scoops.
Scoops.
Mm.
And the ultimate goal there is an initiation interval and 2 of 1.
Meaning a new iteration of the loop begins on every single clock cycle. Massive throughput.
This raises an important question, though. That relies on predictability. What if the code has unpredictable memory accesses? What if things resolve dynamically at runtime?
They used to completely break HLS. Static HLS acts like a VLIW processor. It plans a rigid schedule. If there's a chance of a memory conflict, it forces the hardware to stall.
It just tanks the performance.
It really does. But now we have dynamic data flow circuits. They operate much more like modern superscalar processors.
So they use dynamic scheduling.
Exactly. Using load store queues and FIFOs to resolve dependencies on the fly.
So if a piece of data isn't ready, it doesn't freeze the pipeline. It just executes subsequent instructions out of order.
It avoids those massive bottlenecks, bringing the dynamic flexibility of software right into the raw silicon.
It's a huge paradigm shift. We've gone from 64 simple logic blocks in 1985, manually routed, to heterogeneous AI platforms dynamically scheduled from C++ code.
It's hard to overstate how far we've come.
And whether you're listening to prep for a meeting or just because you're insanely curious, understanding this EDA software to hardware bridge is the key to grasping the future of customized computing.
I completely agree. And I want to leave you with one final thought from the text that builds on this. The text mentions natural level description.
Using human languages like English to describe devices.
Right. It's the ultimate unsolved frontier. Imagine a new future where you don't even need to write C++. You just speak to an AI.
Describing the digital accelerator you want in plain English.
And the EDA tools instantly handle the layout of millions of logic gates, optimizing the power, the timing, everything.
If the only limit to hardware design was your imagination, not your coding skill, what world-changing chip would you build first? Something to mull over next time you look at the silicon powering your phone. Thanks for taking this deep dive with us today.